Hello Year 11, welcome to lesson for exercise 10.8, the language of polynomials. This exercise is just going to cover some basic definitions and vocabulary. So, the definition of polynomial is that it's an expression of the form p of x is equal to this. Now this is just an expanded version where we list all the x terms with its power and its coefficients. So all these a at the front of x will be the coefficients, of course, but we just use the subscript to describe its order number. So if I say a0, for example, we would just call it the 0th a. If it's got a subscript 1, that's just the first a. And then at the beginning, we have a subscript n, which means nth a. But we've listed at the front because it's meant to be the coefficient matching with x to the power of n, where n is a positive whole number, and that's usually the highest power amongst all the terms. So we try to list it so that the highest power term of x comes at the front, and then any x terms that have a lower power comes after in descending order. So then if you have any constants, that's going to be listed at the end of the expression. Let's have a look at some of the key vocabulary. So all these words you're expected to know before we begin the chapter. You were supposed to have covered it in year 10 5.3, but it's good to remind yourselves. So have a read of the words and the definitions and see if it understands. See if you understand it. Now looking at those definitions, let's have a look at a quick example. If I have a polynomial p of x, 3x to the power of 5 minus 8x cubed plus x squared minus 7. My leading term is going to be the term with the highest power on the variable. So if I have a look at my x's, the highest power term I have is 5 there, so that whole term will be my leading term in that polynomial. If the question asks for the leading coefficient, then it will be the coefficient of the leading term, so it's 3. It is not the highest coefficient, it's the coefficient of the leading term. If the question asks for degree, we often say dig p of x, which is going to be the highest power on the variable. The highest number I can see is 5, so the degree of the polynomial is 5. And whether to call it a monic or not. Well, the leading coefficient has to be 1 for a monic polynomial, but this one has leading coefficient of 3, so we can't call it monic. And in which case we call it non-monic polynomial. So those are the words we can use to analyze a polynomial. Now these words down at the bottom, roots and zeros, they're meant to be the solutions to the polynomial, but a lot of the people get confused between those two words. But you can only use the word root if you're talking about a solution to an equation. So it has to be an equation, not an expression. Whereas the word zero can be used for an expression because we are assuming that you're solving for an expression is equal to 0. So for example, it's not going to, it never makes me change the colors of my pen. Say if you have an expression like this, then because it doesn't have an equal sign, I can't say find the roots of that expression. That just doesn't make sense. I could say to find zeros of that expression because then you're assuming it's equal to 0 and then giving solutions to that equation. And then if I say it's equal to 3, then it is an equation, so I can say find the roots of that. To tell you to find zeros of that equation, I guess one side isn't equal to 0, so I wouldn't really say that. I would use the word root in this case, but if they do tell you to find zeros, that probably means to make one side equal to 0 and then solve. So yeah, do not use the word root if it's not an equation. Now we've got some names for polynomials depending on the degree of the polynomial. So for a zero polynomial, it's literally when there's no term in a polynomial other than the constant 0. And it's pretty rare that we have a case like that, so it's not a popular one. We call it a constant polynomial if there are no terms that have x in them. So if I have a single constant, we call that a constant polynomial. Very straightforward. Linear polynomial would be polynomial of degree 1, so that's going to be in the form of ax plus b. Or I could just say the degree of polynomial is equal to 1. Quadratic, that would be when the degree of the polynomial is equal to 2. So then it's going to be in the form of this. And then it's pretty straightforward. Cubic would be when the degree is 3. And quartic gets less popular, but it's when the degree is 4. And then we've got other names, but obviously when it gets more than 4, you're very unlikely to see a polynomial of degree more than 4. So you would just call it a polynomial of degree whatever. Oh, there we go. I wrote it down there. You can just call it a polynomial of degree n, where n can be any positive whole number. Cool. Now for this exercise, I'm not really going to set you a homework, but if you are able to do all the questions in this video, like where I'm just listing it right now, should be good enough. I think question 1, I'll go through it with you. And for the rest of the questions, I think you're good to do by yourself. Question 1 says, state whether or not each expression is a polynomial. Now, for an expression to be a polynomial, we need to have n as a positive whole number. You should have talked about it last year. So for A, the powers on the x are 2 and 1. So this one can be identified as a polynomial. Whereas if you look at part B, the first term can be written as x to the power of -2, and that is a negative index, and a polynomial is not identified for negative powers. So this one is actually not considered to be a polynomial. If you have a look at part C, x inside a square root can be written as x to the power of half. Again, a polynomial isn't defined for a fractional index either. So beep, that's not a polynomial. So then that sort of gives it away. Part D, it's got a fractional index. Nup. If you have a look at part E though, the power on the x is 2, and the power on the x in this term is 1. I know there's a square root on the 3 and the 5, but they're actually the coefficients, and there are no conditions for the coefficients in a polynomial. We've only got restrictions on the power of the x. So this one is defined to be a polynomial. Now F, 2 to the power of x. Polynomials are defined to be powers, defined to be an expression consisting of terms with x to the power of n, not a number to the power of x. That's clearly an exponential expression, so this one cannot be identified as a polynomial. And then you can try the rest by yourself, but just to give quick answers, cubic, of course it's okay. It's not in the expanded form, but it's still a polynomial. This one is a fraction, but it's okay because that's a constant. And that's just the same as having a fractional coefficient. The powers on the x are positive whole numbers. All good. This one, clearly not a polynomial, it's a logarithmic function. Now this one, you just have to check the powers on the x. So power 3, power 2, power 1. Doesn't matter what the coefficients are, it is a polynomial. Constant polynomial. Having a variable on the denominator, so that's going to end up having index of -1 at some point, if you simplify it, not a polynomial. So it's important that you know the definition of what a polynomial is, and you should know how to identify what's a polynomial or not. So for the following questions 2, 3, and 6, I think you guys can do it by yourself. So give it a go. You can pause the screen now and do it, or you can just come back to it later. Next dot point, factoring simple polynomials. We didn't get to the factor theorem yet, so you should only be able to factorize easy expressions. For example, for this one, it's one of those expressions where you can pull out a common factor of x, then the expression in the second bracket is a quadratic, and we all know how to factorize a quadratic. Should be an easy factorization of x minus 10 and plus 2. Easy. And then see how it says write down all its zeros? So it's not an equation because we've just simplified an expression, but you can assume that you're solving for this. Hence, your zeros will be 0, 10, -2. I don't think I have to do BCD. You guys can try it by yourself. Next, identically equal polynomials. This one's also straightforward, but say if you're given that the polynomials are identically equal, then you should know that for any terms that have the same power, as in if you're comparing x squared and x squared, their coefficients should also be the same. And I think that's pretty straightforward. So for part A, for example, I'm comparing coefficients of x squared and saying that a should equal 3. I'm comparing coefficients for the linear term and saying b should equal -4. And I'm comparing the constants and saying c should equal +1. That's all you have to do. And this trick's going to come in handy for harder questions later on, but this one's a very easy application. And you guys can try BCD by yourself. Last dot point of the lesson. Now, we've already talked about degree of polynomials, but sometimes the question is going to ask you to think about what happens when you start adding, subtracting, multiplying, or dividing polynomials. So let's just consider two functions, fx that has degree n and gx that has degree m. What's going to happen if we add two polynomials and try to find the degree of that result? Is the degree going to be n or m? Now I've actually pre-written all the answers so I don't forget. I don't know if you guys can see in the video, but I can highlight to reveal the secret answer. So if you add fx and gx, whichever higher one the degree is, will be the resulting degree as well. So if n is higher, the resulting degree would be n. If m is higher, the resulting degree would be m. Except when the terms have the same power and they cancel away each other, then it might be decreased. So I'll give you an example of that. Say if you've got f of x as a quadratic term like this, and then you've got g of x as a linear, let's say. If you add those expressions, you're still going to get a quadratic. So the degree will be 2. Now, if I have another quadratic, depending on which one I have, if I had this quadratic and add them together, still quadratic. But if the gx that I had was a quadratic that looked like this, then the quadratic terms will cancel away and you will actually be left with linear. So I guess you could say that you will, at a maximum, get a higher number between n and m, or you can just say that it could be decreased like this. That would be my full answer. Now I can, Nope, that's not going to show at all. Maybe I'll just make it blue. That looks ugly, no color. Okay. Now if you subtract the two functions together, that is actually going to result in the same outcome as well, because adding and subtracting, pretty much the same thing. Bloop. What happens if you multiply two functions? Think about that. If you remember index laws, then you might sort of get a hint from it, but if we multiply the two functions together, you will end up multiplying the leading term of fx and leading term of gx at one point. Hence, the degree will be n plus m. Because when you multiply the terms with the same base x, you end up adding the indices. So then what would happen if you divide the two functions together? You would probably get the degree of n minus m. Now that's because I put f on g. If I had put g of x over f of x, that would be m minus n, the other way around. And that is pretty much it for the theory. So as I said, there's no homework for this exercise, but I guess technically there is. Just go back to these questions, and whatever questions I haven't completed, you can complete it in your own pace, and you can check the answers on the Cambridge textbook. And that is it. So I'll see you in the next exercise. Bye!